So, in the last class we defined PRG, then hardness of two types, average case, worst case hardness of any Boolean function. This hardness, remember, will be in terms of circuit hardness. Okay, so that is harder than actually the concept of hardness is harder than about algorithms. Okay, this is about Boolean circuits. Now our goal is, and it will remain this goal for the remaining course, to connect circuit hardness with PRGs, and we have already shown that once you have a PRG you have some kind of de-randomization. So, this hardness will be for circuit hardness, and moreover to get practical PRGs we will need actually explicit function which is hard. So, it will be circuit and it will be explicit. Okay, so remember these two terms. Explicit means that your function is computable in a decent amount of time on Turing machines. There should be an algorithm. Okay, it should not be just an arbitrary Boolean function, but it should be somehow computable. Usually we will say that it is computable in E 2 raised to n time. Then we had defined average case, worst case hardness, and currently it is an open question to find natural or explicit Boolean functions which are super polynomial hardness. Worst case, average case, everything is open. Although we know that most of the Boolean functions are hard. Okay, we know that if you just pick some arbitrary Boolean function, then on n inputs it will require circuits of the size 2 raised to n by 2, but then it will not be, it is not explicit. So, can you think of examples, explicit functions conjectured to be hard? So, the conjectured f of cryptographic significance are, so there are two explicit functions you can think of. One is the problem of SAT. Okay, so what will be the circuit size required for SAT, and remember that SAT is solvable in 2 raised to n time. So, it is explicit enough, but is it hard enough? So, it is conjectured that the worst case hardness of 3 SAT is 2 raised to omega n. Okay, it is believed to be exponentially hard in the worst case, may not be in the average case, but worst case it is believed to be very hard. And second is the problem of integer factoring. So, although it is a functional problem, you can make it a decision problem by saying that given a number you want a prime factor of it, or the smallest prime factor of it, and you want some bit of that prime factor, say the middle bit. So, that prime factor of it, or the smallest prime factor of it, and you want some bit of that prime factor, say the middle bit. So, that way you can make it a decision better than that. Or yes, so what is n? N is the input size, 2 raised to n hard. In fact, there are algorithms better than that. Or yes, so what is n? N is the input size, right? Remember. So, for an n bit number, the magnitude is 2 raised to n. and better than that algorithms are known actually. So it's not believed, it is not exponentially hard, but at least super poly hard we believe in average case. So consider decision version. So later on in the course we will show we'll later prove that worst case hard function implies an average case hard function. So a priori it may not seem possible. You may think that worst case hardness only means that the problem cannot be solved on all the inputs, whereas average case means that on average the problem is unsolvable. Right? That seems much stronger. But we'll actually come up with a very clever technique which can distribute this worst case hardness across inputs, thus making the function average case hard. So that will be the new tool we will study towards the end of the course. So the tool to do this is called local list decoding. Of linear error correcting codes. Okay, so not just decoding, but list decoding, and on top of that local list decoding. So we will achieve this in many steps. That is what our we'll be busy with in the towards the end of the course. So for now, what we will do, assuming average case hardness, we will construct PRGs. Okay, we have already seen that PRGs give you de-randomization. Now we'll go one step back and show that actually average case hardness also gives PRGs. So in turn, and then if when you combine it with worst case hardness with this result to be proved towards the end of the course, you will get that worst case hardness implies complete de-randomization or some de-randomization. Okay, so this topic is called hardness versus randomness. For now, we relate average case hardness to de-randomization. Which is to PRG and then to de-randomization. So what this result philosophically says is that both hardness and randomness cannot coexist in nature. Okay, if hardness is there, then randomness is not really there, and we always mean in terms of efficient algorithms. Any randomized efficient algorithm can be converted into deterministic efficient algorithm, and There are also connections between the other way. So, if there is a PRG, then there is also hardness. So, in that sense, these two are opposites. Okay, this is why hardness versus randomness. So, what is this mathematically? So, let us see the theorem. So, if there is an explicit function, which means a function in E Boolean function, which is average case hard. How hard? Let us say we take this parameter S. So, suppose f is a explicit Boolean function, in particular it is computable in 2 raised to order n time, and it is Sn hard. Then there exists an S prime L PRG. So, the average case hardness parameter S that you will start with, that will be reduced a bit, we will make it S prime, and that much of stretch PRG will exist. Okay, so, to be precise, S prime L will be Sn to the 0.01. And the range of L that we will consider will be around n square. Okay, so this is the precise definition of S prime. So, the stretch that we are looking at L, basically the idea is that we will use this f whose input was n bits to stretch L bits, and L will be around n square, and this L will be stretched to S prime L, which is actually Sn to the 0.01. So, this will be interesting already if Sn was sufficiently large polynomial in n. Okay, say Sn was n to the 1000, then you can see that this will be an interesting stretch. So, this is good for large Sn. So, how do you prove such a result? If somebody gives you a hard function, how do you stretch L bits so that in the image the distribution that you are getting looks random to circuits, small circuits, right? How do you do that? So, remember the definition of PRG. In fact, remember the definition of pseudo random distributions. So, it should look random to small circuits. Okay, so, the way you can use f is that the image of f will not be computable by small circuits because of the average case hardness. So, you use that fact, so that f output looks random, quote unquote random to small circuits. So, use that fact. So, since f is hard, its values look random to small circuits. So, we will use this to our advantage to stretch. We will basically evaluate f many times, and that is how we will stretch L bits. So, stretch a seed Z to 0 1 to the S prime L, and f you will evaluate on n bits, right. So, basically pick sub strings of Z of length n. So, by choosing n sized subsets, I1 to and many subsets, let us say m subsets, and consider f at Zi1, f at Zi2 dot dot f at Zim. Now, this is how you can stretch L bits to M bits by evaluating f many times on many subsets or many substrings of Z. Note that this M bit string has a good chance of looking random to small circuits because the bits seem hard to predict from what comes before. So, hard to guess the next bit by small circuits. And because of this belief that the bits are unpredictable in this string by looking at the prefix, we could say that, or we could expect this string to be a pseudo random distribution. And we believe that the next big bit is unpredictable because naively it would seem that to predict the next bit you have to F inverse, and you have to work with F inverse and then you have to apply F. So, all those things we do not expect small circuits to be able to do. Okay, that is the rough idea, and now we will build on this mathematically. So, take I1 to Im almost disjoint. So, if you take them disjoint, then it becomes even better because to predict the next bit you actually have to evaluate f. The prior information, the prefix does not give you anything, does not tell you anything what the next bit will be. So, you actually have to evaluate f, but evaluation of f is considered hard for small circuits. Okay, so, that is the plan. So, let us formalize this construction in two steps. So, in the first step what I will do is define this m bit string. So, let I be a family of n size subsets of 1 to L. let f be a function. Boolean function. So, from set family and this function, we can define that string, and it is called I comma f Nissan Wigderson generator. Okay, so Nissan Wigderson are the authors of that theorem. So, this idea, we formalize it, we call it I comma f NW generator. This is the function NWIF. It will stretch, it's a stretch function, it will stretch L to m bits. So, Z will be mapped to f of ZI1 dot dot f of ZIM. Okay, those are the m bits. L bits will be stretched to m bits. M is, think of m as much bigger than L. Where Zi is the restriction. Of Z to the coordinates I. Okay, previously also when I said Z sub I1, I meant these positions of Z. So, this NW generator is formalized, and we have to study, and then we have to prove under what conditions is this a pseudo random distribution. So, we will show that actually when f is hard and these I1s to IM are disjoint, almost disjoint, then this is a pseudo random string. But before that, let me define disjointness. What do we mean by that? Let L greater than N greater than D of family I of n size subsets is an LND design if Ij intersection Ik is small. For all pairs. Okay, so we have defined this notion of design, which is really saying that I1 to IM are mutually almost disjoint. We will take D to be smaller, much smaller than L. Now, this Nissan Wigderson generator, the string, we will show that this is pseudo random if f is hard, average key is hard, and the family is a design. So, later we show that for hard f and I being a design, the I comma f Nissan Wigderson generator is pseudo random. Okay, so hardness and being a design suffices. That is how we characterize the randomness or pseudo randomness of this Nissan-Wigderson generator. But before that, we have to show some things. First, we have to show, does a design exist? We don't know whether average case hard functions exist, but we can at least prove that a design exists. So let's first do that. And not only does this design exist, we can actually construct it efficiently. So there exists an algorithm A that on input L and D you have to take, as you can imagine, you have to take the universe to be sufficiently large. So L should be sufficiently large. Take L to be more than 10 n square by D. Don't worry about the exact numbers and the function. This will be clear in the proof. But we have taken L to be sufficiently large so that we have enough points and or elements, and from these elements then the design, the family will be constructed by the algorithm. So the algorithm will output an LND design. I having M will be quite large, much bigger than D as we wanted. So M will be 2 raised to D by 10 subsets in time. Time will also be quite efficient since you are outputting 2 raised to D subsets, and you can expect to go over all the subsets. It will be 2 raised to L time. So there are 2 raised to L subsets of 1 to L, and essentially that is the time to construct this design. It's kind of enumerating, going over all the subsets, right? But it is not trivial. In fact, you don't even see why it exists, because you want so many subsets with mutual intersection smaller than D. So why should such a thing exist? And the size is also only n of every subset. So let's give this algorithm. What is the idea of this? So idea is a greedy approach. Find subset I1, I mean just pick any subset I1 and then pick I2 so that it is sufficiently disjoint from I1, and then I3 pick it so that it's sufficiently disjoint from the previous two, and so on. So greedily build. Greedily build the family I. So initialize I to be empty. Now first step is I mean at some point, say you have already found I1 to IM, or maybe I should use different variables. So I1 to IP. With P, actually I can use M. M is not in the theorem statement, lemma statement. It's just a dummy variable. So with M less than 2 raised to D by 10, So, suppose at some point in the algorithm you have already found m subsets, they are n size, their mutual intersections are less than d, less than equal to d, but the subsets are not enough, they are smaller than 2 raised to d by 10 in number. So, you have to pick one more. So, how do you pick one more? Go over all the remaining subsets. So, find an I in this L, choose n, go over all the remaining n size subsets such that for all j in M, I intersection I j is less than equal to d. So, just check this condition. Okay, find an I such that this condition holds. Now, this I may not exist, we will analyze that situation later, but suppose you find it, then you just include it in the family. And go to 1. That is the algorithm. Okay, it is a simple step by step or a greedy approach. The only issue is that in step 1 at some point it may get stuck, right. So, you have to show that it actually goes all the way to 2 raised to d by 10 iterations. Time that it takes is just simple computation. You are going over all the subsets in one iteration. So, that is 2 raised to L, and subsets are of size n. So, this much time in a single iteration, and the number of iterations that you are doing is 2 raised to d by 10. That is the number of iterations, and this m that you have collected, you will be looking at the intersection of I with them, right. So, that is another 2 raised to d by 10 in every step. So, that is in all 2 raised to order L. Okay, so, time is within bounds as claimed. Can it get stuck at m less than 2 raised to d by 10? So, we will show that that does not happen. It is a surprising fact that step 1 will always find an I. Okay, so, we have to show that in this algorithm, when in step 1 we are looking for an I that is almost disjoint from each of these ij's. In particular, the intersection should be less than equal to d. This always exists as long as m is small, smaller than 2 raised to d by 10. So, we show so it will not get stuck, and we show this, we show the existence of I. So, in step 1 by the probabilistic method. So, what this means is we will now show that in step 1 when you are searching for I, if you do the search in a random way, that will suffice. which in particular will mean that if you do a brute force search, you will find an I, okay, because probabilistically it exists. So, hence it exists. That is the reason. Probabilistic analysis will be easy to do. So, instead of showing it by some other means, we will prefer the probabilistic method. You will see that it is very easy to show. So, build I by picking each element in L with probability equal to 2n by L. Okay, there are L elements. If you did this uniformly, you would have given probability 1 by L, but that will, in the expectation, it will not give you too many elements. Since you want many elements, you want I, you give each element more probability, 2n by L probability, and you pick, which will ultimately mean that expectation is you will be picking many elements. That is the probabilistic process. Now, let us analyze this process. So, what you can write is that expectation of the size of I, expectation is, you can write this as a sum over all x's and the probability of picking x. Which is equal to sum x 2n by L, which is equal to 2n. So, in expectation you are picking 2n elements. This is just by the definition of expectation. Moreover, for every j, what can you say about the intersection of I with ij? What is the size of this? I intersection ij. So, this is again you do it element by element. What is the chance that x is in ij? So, in fact, x is already in ij. We will only do this. This only makes sense for elements in ij. So, that is the universe now. And in that probability that x is picked. So, which is size of ij, that is n, times probability, which was 2n by L. Right. So, this is equal to 2n square by L, and what did we say about 2n square by L? So, we have assumed that 2n square by L is less than d by 5. Okay, so, the intersection size is expected to be small, smaller than d by 5. So, this process is doing good, that is what you learn. So, what remains to be done is we have to compute the probability or estimate the probability for this size of I being n. It is a probabilistic process. So, there is a chance that the size of I is smaller than n. If it is bigger than n, it is okay, because we can just drop elements more than n. But if it is smaller than n, then it is not a good, it will not work for us, because we wanted I to be n subset, n size subset. And similarly, what if the intersection of I with ij is more than d, right? Again, this process is a probabilistic process, so it may give you I intersection ij more than d. So, we have to estimate those probabilities, and that we will do by Chernoff bound. So, recall Chernoff's bound. Chernoff bound says that the probability of a random variable deviating from the mean by a lot. So, x minus mu being more than c times mu. So, this is the mean. So, this probability you expect to be small, but Chernoff bound will give you very specific estimate. It will say that this probability is less than equal to 2 times e to the minus mu minimum of c by 2 and c square by 4. Okay, so don't worry too much about this min c by 2 c square by 4 part. Think of this as e raised to minus mu c. So, what this is saying is that the deviation away from the mean by a multiple of c is exponentially falling. It is e raised to minus c mu. Okay, so this probability is exponentially small. That is what Chernoff's bound says, and you can also prove Chernoff bound. Maybe we will give this as an exercise. This is an important and very useful estimate in probability, and now we will use it. So, now we will relate, so remember mean and expectation are the same, right? So, we have computed the expectation, and now we will compute the deviation. So, now by Chernoff bound, probability that size of I is less than n. So, how much is the deviation from the mean? So, this is same as saying that probability or at most probability, so size of I minus 2n, this value, this magnitude is greater than n, right, because mean, remember expectation is 2n, that is what we have shown. So, if the size of I is less than n, then you are saying that the deviation is more than n, and by Chernoff bound this will mean, it will mean that less than 2 times e to the, yeah, so let me write it in the correct form. This is half of 2n. C is equal to half, so you will get 1 by 8. You will get right 1 by 16 times 2n, which is 2 e raised to minus n by 8. So, point being that this is exponentially small. In terms of n, this is a very small probability that size of I will be smaller than n. It will be n or more, which is good enough for us, right? We wanted n subset. Similarly, for all j, the probability over random I by the process given above, the size of I intersection I j being more than d this probability is, so what is the intersection size expectation, that is less than d by 5, and you are, the event here is greater than d, right. So, deviation is more than d minus d by 5. So, this is 4 times d by 5. That is what is happening. So, from the mean, the deviation is more than 4 times the mean. So, this is again a situation good for Chernoff bound, and Chernoff bound will give you here less than 2 times e to the minus d by 5 times 4 by 2. Okay, so, you get these two probabilities. As you can see, both are exponentially small. So, now what you get is the probability over this process to construct I of size of I being less than n, or there being some j with which the intersection is large. Okay, this probability is less than, use the union bound. For the first you will get 2e minus n by 8. For the second event, it's a, there exists j for m many j's, right. So, m times 2e minus 2d by 5, which is m is smaller than, you are assuming m to be smaller than, you are in that situation, 2 raised to d by 10, right. So, in step 1 m is smaller than 2 raised to d by 10. Okay, which is overall less than 1. For large enough n and d, this sum is actually very small, much smaller than 1, and that means that the probability over I being greater than or equal to n, and for all j intersection being less than or equal to d, positive. It's a positive probability, so which means that in step 1 I exists. So, implies that the algorithm constructs I. Okay, so, this algorithm, which is actually a deterministic algorithm, it will all, the step 1 will keep finding I, and ultimately it will give you this family, which is an LND design in 2 raised to L time. Okay. So, once you know that design is not only there, but also constructible this way, what you can do is use the Hart function f, right. So, we were here, we had defined this Nissan-Wigderson generator, IF NW generator. So, we will now use I1 to IM from the design, and f this average case Hart function, and we will study the string of m bits. the stretch from L to M. We will show that that is a pseudo-random distribution. We use the design in IF and W generator. So, we will get this lemma 2. So, if I is an L and D design, with the size of I 2 raised to D by 10, let us call it M, F Boolean function which is average case hard. So, the hardness we are assuming to be 2 raised to 2D. So, if I is an LND design and F is average case hard with parameter 2 raised to 2D, then this NWIF generator, the image of that on random L-bit strings. So, this distribution that you get is pseudo-random. This is the parameter So, two circuits of size this parameter each, the hardness of F divided by 10, and we cube it, right. So, the cube of this, two circuits of that much size, Boolean circuits, they will not be able to distinguish this Nissan-Wigderson output with the uniform distribution better than the probability distribution will be actually worse than 0.1. Okay. So, you can say in simple words that Nissan-Wigderson output is pseudo random or looks random to small circuits. So, why is that? How do you show this? So, suppose not, it is a proof by contradiction. Suppose there is a circuit of small size that is able to distinguish this from UM. Distinguishes NWUL from UM. If there is a distinguisher circuit, then the way this NWUL is defined, it is this M applications of F on the design, right. We will show that we can predict one of these bits, then we can design a bit predictor for F Z I J. We will call it I 0. for fzii for some I. And design a bit predictor circuit will be C prime, and this will be a contradiction to the hardness of F. The average case hardness of F. Okay, this will be our so the overall sequence of arguments will be like this, that if there is a distinguisher for NWUL versus UM, then that distinguisher will actually give you a bit predictor, and that bit predictor will have a small size, and that will be in contradiction with the hardness of F. Okay, so let's start this. We'll finish it next time. But let's start some implementation of this idea. So let S be the average case hardness of F. Suppose there exists circuit C of size less than equal to S by 10 such that the probability of Nissan-Wigderson distribution. So, on this distribution C being 1, what is the probability of that? That is one probability, and second is what is the probability of C being 1 on the uniform input distribution. Okay, so remember we try to C is we are claiming that, or we are assuming that C can distinguish between these two distributions, stretch of UL and UM. So, suppose this probability difference is more than 0.1, at least 0.1. So, this is that is NWUL is not pseudo random. Then there is a distinguisher C, circuit C, and we can assume that this difference is actually positive and at least 0.1. It's magnitude, right? So, you have to consider two cases. It's positive more than 0.1, or it's negative and less than minus 0.1. So, let's assume this case it won't matter. I mean, the proof is the same for both. Okay, so without the magnitude symbol, magnitude operator, this is already at least 0.1. We will now devise a bit predictor as promised. For NWIF. Okay, so this we will finish in the next class.